Coastal erosion is often perceived as a scene of chaotic destruction. We see cliffs crumbling and land receding, seemingly at random. However, modern telemetry reveals a different story. Erosion is not random, it is a structured, recursive process. We can reframe every collapse as a rigorous, iterative mathematical computation performed by the Earth itself. It is a calculated minimization of energy. The coastline paradox shows that as our measurement scale decreases, the measured length increases toward infinity. The coastline paradox shows that as our measurement scale decreases, the measured length increases toward infinity. The coastline paradox shows that as our measurement scale decreases, the measured length increases toward infinity. This proves that shorelines are not simple geometric lines, but complex fractal curves with infinite detail. In 2026, a major breakthrough in satellite telemetry transformed how we study coastal erosion. We have moved from theoretical modeling to precise, empirical observation. Advanced satellite arrays now provide sub-centimeter resolution, allowing for real-time analysis of cliff disintegration. Previously, cliffs were too irregular to quantify. Today, high-resolution data reveals the recursive nature of the landscape at a sub-centimeter scale. This clarity enables scientists to calculate the fractal dimension of a coastline instantly. It proves that shoreline erosion is not chaotic, but governed by infinite mathematical blueprints. We are now witnessing geology compute its own next iteration. In the study of coastal geomorphology, we observe a phenomenon called self-similarity. A small rocky protrusion often mirrors the geometry of the entire headland. By isolating this segment, we find that the structural complexity is repeated across different scales. This recursive pattern is the unmistakable signature of a fractal system in motion. Whether viewed from satellite altitude or the shoreline, the statistical probability of these shapes remains consistent. Geology computes its own next iteration, ensuring that nature's blueprint remains mathematically uniform. The Norwegian fjords act as a geological hard drive. Their serrated, self-similar edges encode centuries of history. These jagged rock walls possess self-similar patterns, repeating the same geometric signature at multiple scales. Each serration records data points about sea level fluctuations, preserving the past within the mathematical structure of the rock. Waves are not just water. They are massive inputs of kinetic energy. When this energy strikes the coastline, it acts as a variable in the Earth's geological equation. Each wave collision provides the energy required for the cliff's recursive calculation. The cliff essentially processes this input to determine its next geometric state. This process is a continuous loop where fluid force meets mineral resistance, creating the complex fractal signatures we observe today. In the recursive calculation of coastal erosion, the rock itself acts as a variable. While fluid energy is the constant input, the mineral composition determines how the cliff breaks down. Consider two different cliffs. A porous rock like chalk offers low resistance, leading to a high-density fractal branch pattern. A dense rock like granite resists the iterative force, resulting in a much coarser, simpler signature. These varying responses to tidal iteration create unique fractal signatures. The chalk cliff crumbles into complex, self-similar geometry, while the granite cliff maintains large-scale structural stability. By defining sedimentary resistance as our variable c in the recursive equation, we can finally predict how different coastlines will evolve over geological time. Why do coastlines erode in such jagged patterns? It is not merely decay. This fractal shape is a highly optimized geometry designed by nature to manage kinetic energy. When wave energy strikes a smooth surface, the impact is concentrated. The cliff bears the full force at a single point, leading to rapid, catastrophic structural failure. In contrast, a fractal cliff acts as a natural shock absorber. Its jagged geometry sprays impact forces across multiple edges, diffusing the stress rather than concentrating it. This structural efficiency prevents total collapse. By iterating into a fractal form, the coastline preserves its integrity far longer, performing a complex recursive calculation of stress minimization. By 2026, the study of coastal erosion has evolved from reactive observation to predictive modeling. Scientists now calculate the unique fractal signature of a shoreline to understand its structural blueprint. By identifying the fractal dimension of a coast, we can now forecast future recession patterns with high precision. This allows researchers to see the path of erosion over the next 50 years before it happens. Geomorphology is no longer about guessing the future of our cliffs. It is about decoding the mathematical language in which nature writes its own history. Traditional seawalls are often flat and rigid, acting as a blunt barrier against the ocean. While strong, these structures reflect wave energy back into the water, often causing erosion at the base, a process known as scouring. Engineers are now pivoting toward nature-based solutions. By designing breakwaters that mimic the complex, self-similar geometry of natural cliffs, we create surfaces that dissipate kinetic energy more effectively. When waves strike these fractal patterns, the energy is scattered and trapped within the structure's voids, rather than bouncing directly back. This reduces pressure and helps maintain coastal stability. By replicating the fractal dimension of natural coastlines, modern engineering turns structural resistance into a rhythmic, energy-absorbing harmony. Recent 2026 data reveals a startling truth about coastal processes. Across the globe, geography is not behaving randomly. In fact, 88% of major erosion sites demonstrate a stable fractal dimension. This suggests that the collapse of a coastline is not an act of chaos. Instead, the Earth follows an iterative, mathematical blueprint. The stability we observe indicates that even at the point of destruction, geological forces operate within a strict, predictable system. The masterpiece thesis redefines coastal erosion. As Dr. Elena Vance states, geology is computing its own next iteration. We are not witnessing the death of nature. Rather, we are watching the Earth perform a complex, iterative minimization of energy. By viewing coastlines as mathematical equations in flux, we recognize the beauty in structural transformation. Comparing the Mandelbrot set to a coastline reveals a deep, underlying structural unity. What we see here is not coincidence, but the result of recursive branching. On the left, the mathematical iteration of a function creates infinite complexity. On the right, the iterative force of tidal energy against mineral resistance creates the same self-similar branching. Both systems operate under a power law distribution, meaning the edge density remains statistically consistent regardless of the scale of observation. Geology mimics the hidden blueprint of mathematics, computing its own next iteration through the persistent feedback loop of kinetic energy. A fascinating characteristic of nature is how it packs infinite complexity into a finite boundary. This concept is the cornerstone of fractal geometry. Consider a segment of coastline within a finite area. At a low resolution, it looks like a simple, measured line. As we increase our level of observation, we reveal hidden bays and rocky crags. The path becomes longer, even though the total space remains the same. This process continues endlessly. Each zoom reveals more texture, effectively making the perimeter approach infinity while staying strictly within these bounds. This mathematical paradox explains why our shorelines look so remarkably detailed no matter the scale of observation. The coastal erosion process is governed by recursive functions. The equation z sub n plus 1 equals z sub n squared plus c represents the iterative interaction between waves and land. The constant c acts as an environmental variable. In geomathematics, climate change and shifting tide levels directly modify the value of c, effectively altering the input of the recursive function. As climate impacts shift the c constant, we observe an acceleration in fractal growth. The shoreline does not just erode, it evolves through a different mathematical pathway, leading to more complex and often more rapid structural disintegration. This explains why coastlines are increasingly unpredictable. Changing sea levels change the geological computation, forcing the land to find a new state of stability through accelerated iteration. We often perceive straight lines as the hallmark of order and precision. However, in the physical world, the straight line is merely a human construct, a geometric ideal rarely found in nature. When subjected to the relentless iterative forces of tides and fluid dynamics, a perfectly straight boundary is physically unstable. It forces energy into a single linear concentration, leading to immediate fracture. Nature bypasses this by utilizing fractal geometry. By branching and iterating, an interface distributes energy across infinite points, creating a state of structural equilibrium between the air, the water, and the solid rock. Straight lines belong to the mind, but fractal iterations are the blueprints of the living Earth. Every stretch of coastline possesses a unique structural fingerprint. To map this, researchers isolate specific segments and analyze their boundary geometry. By applying a grid at varying scales, we calculate the fractal dimension, d. This measures how the perimeter changes as we observe it with increasing precision. This ratio defines the complexity. A constant d value for a specific region acts as a mathematical signature, stable even across centuries of erosion. This signature allows us to classify geography not by sight, but by its deep, recursive mathematical blueprint. This ID represents the specific identity of this cliffside. Our study of the Earth has fundamentally transformed. Historically, geology was a static discipline. We focused on mapping precise locations, treating the coastline as a fixed, rigid boundary on a map. Today, we view the shoreline not as a place, but as a process. By applying recursive mathematics, we track the iterative feedback between tidal energy and sedimentary resistance. This evolution shifts our focus from documenting decay to computing the iterative path of coastal change. We no longer just map geography, we map the mathematical blueprints of its transformation. We often admire the craggy, jagged beauty of a coastline as a work of chaotic natural art. Yet this visual texture is the direct product of a rigorous, infinite mathematical calculation. Every indentation and cliff face is the visual signature of an iterative feedback loop. Fluid kinetic energy acts as the input, while mineral resistance acts as the variable. What we perceive as raw disintegration is actually a perfectly executed infinite blueprint. The Earth computes its own shape through time. In this journey, we have explored the coastline not as a static edge, but as a dynamic, recursive computation. The cliffs you see before you are the final output of an ancient infinite calculation. Consider the sea as the processor, tirelessly iterating through the laws of physics. Each wave is an input, refining the geometry through constant feedback loops. The result is a masterpiece of fractal geometry, where chaos is tamed by the rigors of energy minimization. The next time you stand before the ocean, remember you are witnessing geology computing its own next iteration. You are standing before the infinite blueprint of our world.